feed them with data and get the results out of it. Let's go a little bit into detail. We make like a zoom to the VOD model. How is such a model built up? First of all, we have the core model, which is like more or less just related to the process. Ladle furnace, VOD, electric arc furnace, like that. And the VOD core model consists of a modeling pipeline. We call it pipeline because you can imagine that you have more sub-models. For example, in the VOD unit, you can have decarburization. You also need to consider the hydrogen loss during the vacuum itself, a temperature model, and you can separate those little sub-models and just build up a pipeline at the end. And when you now execute the model, this pipeline will be executed and throw out the result at the end. Let's go into one sub-model. A sub-model at the end is built of modeling blocks. Why we use this approach? Because metallurgists and physicians, these guys are used to create flowcharts. It doesn't make sense to tell them they should create a piece of code as a specification. So usually they give you a kind of flowchart to present you what the model should look like. And at the end we try just to do the same in the source code as they do in the specification. So one submodel just consists of these modeling blocks, and they will execute it according to the data flow which is designed. And now I'm going to show you how such building blocks of a VOD, in this case it's the decarburization submodel of the VOD process. How does that look like? First of all, we have like initial conditions. This is depending on or offline simulation. In online, it's the process data. It's like the input. And also in offline simulation, it's the process data. Because for offline simulation, you can use the Inteco level 2 system to export some heats that you have already produced in the past. And then you can check with this exported data, you can go into the runtime, into the offline simulation runtime, and just change some parameters and check what's the result now. And then actually the sub-models, the model blocks are going to be executed. Starting with oxygen distribution, then checking if we're like in the stoichiometric or kinetic mode. At the end, making the mass balance, checking the temperature, and that's it. The colors refer to the first slide of this modeling library, because the slag activity which is called here is part of this fundamental. Is part of this fundamental based core library on the bottom. The green ones are these modeling blocks inside a submodel, and the gray parts, this refers to the responsibility of the runtime itself to feed the model with the right data. That means that the runtime of online modeling is responsible to create the conditions to collect the process data and feed the model. In offline, the runtime is responsible to extract data from a database or whatever data source you want to use to feed the model. So therefore, the result here, the condition of the steel, goes back to the specific runtime, and they are responsible to keep the image, the state of the heat up to date. So now you may ask, where is now the submodel itself? Because I was talking about submodels and modeling blocks. You see here the runtime fundamentals, modeling blocks. The submodel is now this what I made here in this gray scheme. So everything inside here is like in one submodel source code. And these modeling blocks will just execute it through this. In this case, it's a conditional statement. This one is just sequential statements. So, how can you use now this model library at the end? There are two ways to use it. The first approach, you have a model library, and you export this library in. It doesn't matter actually which programming language you use. You get a package, You can now integrate this package, this model library, directly into the online application, which is our IMAS system, level 2, and you can integrate it directly also in the offline application. That means it's like a library which is directly integrated. The advantage is the performance is a little bit better, but you have to develop it in the same programming language. Second approach is to host the modeling application as an own application and just call the JSON or a web API, which is platform independent, and whatever software you have here, you can just call our modeling suite and yeah, use it in that way. That makes us really open for also existing level 2 systems all over the world, and also for offline simulation. So we can just prepare the models as know-how, and yeah, feed whatever system you have. At the end, some results and installations, some figures, because I know that talking about modeling and software is always a kind of abstract and hard to imagine sometimes. Over the last 1.5 years, we made 2 greenfield projects as Inteco in Taiwan and South Korea. They have a 130-ton electric arc furnace spatial steel shop for high alloyed steels. And in Frisa in Mexico, they also built a completely new steel shop, 50 tons electric arc furnace. And in both cases, we installed our level 2 system, including this model library, including this approach. And the challenge there was that in Taiwan and South Korea, we were forced to install our old level 2 system. And in Mexico, we developed the second version of our level 2 system. So totally different source code bases. And now the challenge was to integrate the same models in both libraries, in both systems. This picture shows our new level 2 system for Mexico. And what you can see here is the ladle furnace. And the result of the model library is shown in this curve, which is the temperature. And these little dots are actually the measurements. So you can see that the prediction was pretty close. Next one, that was a diagram of the VD unit, degassing unit. What you can see here is also a prediction of the temperature. In this case, the model didn't consider that it was a brand new steel shop and a brand new ladle, and the preheater, the burners of the preheating was more to just start a cigarette, but not to heat a ladle. So the flame was really short. The hydrogen content, as you can see here, we predicted this value compared to the measurement at the end, also pretty close. So you see the result of the online simulation goes directly into this new level 2 system. Compared to this, you can see directly on the HMI, on the old system in South Korea. But at the end it was the same results. We installed our modeling library, they called the API, and got also the temperature curve in that system. Also, hydrogen is the same thing. Ladle furnace and VD unit. In this case, this is the hydrogen curve. And at the end, some results of the offline simulation, because both of those applications before were online inside the level 2 system. This one is our offline simulation tool, which is also, of course, using this library. And what you can do here is like to configure a simulation with the exported data from the level 2 system. So you have already produced some steel, you have produced some heats, just get the data out of it and try to make your models to fit that data. That doesn't mean that it's working also in the future, but according to this data that you have already produced, you can fit the model. And I can show you here what we did in South Korea. We just installed the model library, and our VOD model was pretty wrong, let's say it like that. Why? Because the parameters were not tuned or adjusted to the conditions in South Korea. So what you can see here is that one is the temperature curve of the real data. So during the production of the heat, we predicted this temperature. and here was the correction. So they made a measurement and it was like, I don't know, 40 or 50 degrees higher. And then we just changed offline some parameters according to the conditions in South Korea, run the simulation, and the result is this curve. Because as you can see, the problem was that we considered the temperature loss during due to the oxygen blowing was just too high. And so the temperature that you gain here is much higher, and as you can see, just because of the tuning of the parameters, we just hit this measurement at the end. So that was my talk about modeling, software development, challenges in this field. I'm on the end now. I want to thank you, and I also want to take the possibility just right now, because Roland and myself, we are like in a tight time schedule, so we have to leave today. I want to thank all of you. It was a great conference. Thank you for the organization. It was really a pleasure to be here and meet so many nice people. Thank you so much.
Thank you for your presentation, very interesting. And from our side, from the side of the organization, we want to thank you that you are with us here, working. I think your presence here increased our goodness of our conference. So,
oh, thank you. Great.
So
we definitely want to come back. Yeah, that's pretty clear for me. Ukraine is a nice country.
Thank you. Welcome next time.
Thanks.
Questions, please.
Nothing. I was expecting some questions.
We can discuss later.
Perfect. Yes. Okay.
For your presentation.
Thank you.